In the previous lecture, we studied the contact between metals and semiconductors, meaning the solid materials. In lecture 10, we are going to study the when the electrodes has a contact with solutions, meaning the chemical species. So let's first check up some of the terminology, and also, and again, I would like to remind you, this is a case when we use electrode has a contact with having a contact with solution, right? So at first, I'll show one of the typical semiconductor materials. This is a case, especially for the case of titanium oxide, which is most frequently used semiconductor materials in a photoelectrode. And here you will show, you've already studied the work function, which is defined by the energy necessary to extract the electrons from the solid materials, right? But this work function is basically measured in a vacuum condition. So in this figure, the electron lies around somewhere in a Fermi energy level, as we studied. So what we have to measure for as a work function is the vacuum level energy to the Fermi energy, which is somewhere around 4 to 5 electron volt. As a terminology, as a custom of this, it is used as negative value. But anyway, you need a 4 or 5 electron volt to extract the energy to the vacuum level. But if this material is in a solution and used as an electrode, we use this energy level is controlled by the bias voltage, and the bias voltage, if you apply the voltage toward the downward, so meaning that Fermi energy is pushed down by applying voltage, it is called anodic potential. Then, in this case, Fermi energy will move downwards. And oppositely, and then this one, I would like to emphasize that this one is taken as positive. So it's opposite, right? So if you apply the positive potential, meaning anodic potential, the Fermi level is pushed down. And oppositely, if you apply the negative direction, it's called the cathodic potential. So in this case, Fermi energy moves upward. And also, I would like to emphasize that in the electrochemistry, we set the 0 volt at standard hydrogen electrode potential, which means hydrogen is changed to a proton, which is in electrochemistry, the redox potential is zero, is defined as zero, which is the SHE. And this SHE is correspond to the 4 or 5 electron volt. Of course, these two measurements are different. The one is measurement, work function is measured in a vacuum, and this electrode potential measurement is the electrode must be in a solution. So there's no direct contact, but there are many studies to correlate this energy. Anyway, both of them measure the energy level or energy level control. So they have some correlation. And which was like 0 volt is somewhere around -4 to 5 electron volt. Okay. And similar as the semiconductor metal or semiconductor contact, I would like you to remember that the electrode, when the electrode has a contact with a solution, right? Solution, somewhere the electron at Fermi energy, right, are given or taken depending on the Fermi level or redox potential of the species in solution, right? So in the case of semiconductor case, depending on the height of the Fermi level, the electron is given or taken by these materials. So the basic idea is same. So let's check up what will happen for the N-type semiconductor. Okay. So I would like you to remind that. So again, here, the difference is here. So we have some solution side in this case, and solution includes redox species, which means the accepting or giving the electrons to the electrode, right? So what I mentioned here in this sentence means this redox potential and the Fermi energy of the semiconductor. So depending on this height, this level difference, whether the electron is given or taken is decided. The key point is this redox species is dependent on the chemical species. So this energy level cannot be changed. I want to emphasize this point, because this is decided by the chemical structure. So the energy level of the redox of chemical species cannot be modified. However, in the case of metal or semiconductor, somehow Fermi level can be controlled by applying the potential. So let's think about that. So in this case, there are two cases possible. One is Fermi level is higher than the redox chemical species redox potential. And on the other hand, here, this is redox potential is higher than the Fermi energy. Right? So please stop for a while and think about the energy diagram for this one and this one. How the energy band is changed by having a contact with solution for n-type electrode. Okay. So let's check for the answer. So initially, for an n-type semiconductor, here is a donor, almost around the donor level, and this electron is thermally excited to the conduction band, becoming the charge carriers. However, if you have this one has a contact with a chemical species, since this level is lower, the electrons are given to the redox species. That's why the Fermi level is gradually going down. And the key point is gradually, because as I mentioned, the donor number is limited. So different from metals, it cannot change suddenly the band, right? That's why the band is gradually changed by giving the electrons. So what will happen is like this. So the redox of chemical species cannot be changed. But at the equilibrium, the Fermi level must be matched with the redox potential. And since the band must be gradually lower, like this. This is what happened. And then I would like to emphasize that the electron is given to the solution side. So the n-type semiconductor surface become, since electron is given, so positive charge, positive lattice charges are left. And that's why at the interface, the negative species coming, meaning the anion species is coming to the interface. That's what happened. So as you could see, for electrons, it's a uphill barrier here. And as we studied in the semiconductor contact, it is called a Schottky contact. So this is what happened when the redox potential is lower than the Fermi level. Okay. On the other hand, when the redox potential is higher than the Fermi level, this is also the how to think about this is same. So in this case, now, okay, the electrons, since this one is higher, so electron shift and electrons given to this from the redox species. And then the band is gradually become higher. So based on this, what happened here is the same redox potential of chemical is the same. And at an equilibrium, Fermi level must be similar. However, the band is gradually changing. So this is the original position, like this. And then I like to mention that the charges, since the charge is given from the redox species, the surface become more negative because the donor side is occupied by the electron given from the species. And on the other hand, at the interface, the cationic species are coming to the surface, and that makes like this. And for electron, it's kind of like a downslope, so easy to go to the solution side. So that's, in this case, the contact is called an ohmic contact, similar as a semiconductor contact, okay?